This is a Systemic Complexity and Strategy course, Knowledge Seed number 5. And here we will be looking at the feedback principles. The outline for this seed is going to look at the following topics: feedback loops, principles of systems, define what level and rate variables are, looking at feedback loop behavior, understanding the causal loop diagram or influence diagram syntax, and just to provide a brief overview of some causal loop diagram examples. Now, feedback loops. Feedback loops is the basic structural element of a system. It's very important to understand that and to retain that complex systems are a collection of interacting feedback loops, and that decisions are always made within feedback loops. For example, decisions control an action that changes the levels within a system. And a decision can be part of one or more feedback loops at the same time. What are level and rate variables? Level variables and rate variables are substructural elements of the system. And in order to have a feedback loop, it's very important to have a level type variable because it's a fundamental variable of that process. On that picture, this is a typical, what we refer to as level rate model structure. This is a model representation built within a system dynamics software that's looking at adoption rates for potential technology, for example. And what we have on that picture are the various building blocks of the system that's being modeled. As you see this rectangle, it's there to represent a level state or basically provide data about the level of adoption. Now, the adoption limit is an information on the state or level of the system, and we're comparing that value with other values that go into the adoption rate in order for the system to make a decision. And the rate variable is the decision variable. Now, each of these variables have different units of measurement. For example, a level variable or a stock or a state variable will tell you how many there are in that box. So it tells you about the level of the system. On the other hand, the rate variable will have a value which is per period of time. And therefore it's telling you the speed at which the system changes. Now that speed is also regulated by what we see on top, the adoption delay. Now the adoption delay will regulate the speed at which individuals that are on the left-hand side box, the adoption potential for a market, for example, how fast it will move from that box to the other box on the right-hand side, which give you at the end of the day the level of adoption. So this is a basic simple level rate model structure, but you can see all the building blocks there. The other thing that you see are thin arrows, and those thin arrows are considered connectors, and those connectors carry the information from the levels to the rate and back to some other type of coefficients or information on the state or level of the system in order to create a meaningful representation of the system. Now, levels tend to accumulate the results of actions or decisions over time. And typically they're not changing instantaneously. There are time delays associated with them. And it's one of the characteristics of the system dynamics principles to take into account the passage of time, explicitly into account in computations. And therefore, for a level variable to change, there must be a rate of change within the system that is directly connected to the level variables. And that happens and occurs as a result of the passage of time. Some examples of level variables that you may think about. For example, at any point in time, when you're looking at a system, you will have at times tangibles and intangibles. For example, you'll have number of employees that belongs to an organization, the capital, the equipment, the capacity, and the liabilities, which can be measured in any kind of units, such as, informational units, material, financial, economic type measurement units. While the intangible, it's also possible to have intangible state or level variables. They are things like, could be the level of the reputation, the employee morale, perhaps some index of product quality, perhaps a perception about particular variables within the system. So, particular object. So, therefore, within a system dynamics model, you can take quantitative variables, but you can look at tangible and intangible type variables. How does it work? You've got typically 4 components to an equation. You've got the goal that is set within the system. You've got an observed condition of a system, which means the level that the system is actually at. And then you figure out a way through a variable, that an equation that is appropriate, to calculate the gap between the goal and the observed condition or the observed state of a system. And that gap is going to drive a decision of how the action is based on that gap. And this is how a system dynamics model equation actually works. Now, there are 2 main types of feedback loops. You've got reinforcing feedback loop. The reinforcing feedback loop can be represented using the time graph that you have on the right-hand side of the screen. Now, a reinforcing generates a compounded effect. So it's cumulative, it's compounded effect, and so it grows exponentially, and therefore it can either grow downward or grow upward. And what characterizes the reinforcing feedback loop is that it shows the value from which the system has diverged toward its growth or its decline path. So from there you can observe that exponential growth or decline. Now, reinforcing feedback loops can also be called positive feedback loops, to keep in line with the principles that, mathematical principles that generate them. Now, there's another type of loop which is called the balancing or negative feedback loop. The balancing feedback loop, represented by the letter B on an influence or causal loop diagram, is the value towards which the system is moving, typically towards some sort of goal or goal-seeking or equilibrium value within the system. And therefore what we see is either the path of a variable is going to try to adjust to a given value, upward or downward, depending where it's located at the time of the start of the simulation. So these 2 basically form what we call the basic structure of the system. And in system dynamics, we are looking at closed boundaries or frontier of a models, and within which feedback loop structures exist. And the substructure includes the level and rate variables, which then includes the goal, the apparent state of the system, the gap, and the actions to be taken. Now, to go back to our earlier adoption model, this on the left-hand side is called a structure. And when we're conducting system dynamics work, and what we're trying to do is to look at how structure on the left-hand side influences behavior on the right-hand side. Now, typically, when we have access to data, what we observe are trends over time. And what we're trying to do when we model is essentially to try to see and replicate to some extent, and there could be many extents of that, whether you want to illustrate it from a pedagogical standpoint, or whether you want to explain it by trying to mimic real behavior of a real system. Your degree of involvement then will vary to the extent of what your purpose is. But nonetheless, what you're trying to do is try to capture, using the system dynamics approach, a structure that will replicate or at least mimic to some degree the behavior of the system. Now, feedback loops are represented using causal loop diagrams or influence diagrams. And those causal loop diagrams or influence diagrams, they should be thought as dynamic hypotheses. For those of you unfamiliar with the expression, what that means in the particular context of the application of the principles of system dynamics, what it means is that they represent a view of the system that is posited. That means that it can be challenged, revised, and updated. And therefore, instead of thinking of a representation of a model or a system as a final representation of it, one should think of it as the current view and current understanding of that representation, and therefore subject to revisions based on newer information that will come along. Now, it's important to dwell a little bit on some of the syntax that pertains to reading and understanding influence diagrams or causal loop diagrams. So essentially, an influence diagram or a causal loop diagram is a language that is used to map the qualitative structure of causes and effects of a system. For example, a straight arrow gives you the direction of the influence. So it goes from the cause to the effect. Now, when there's a plus, it means that those two variables move in the same direction. That means if A increases, B will also increase. When you have a minus sign, it means that the cause and the effect are moving in the opposite direction. So if the price of a given good increases, then the demand will fall. These are the kind of opposite relationship. But the logic underlying the relationship between the variables should not be confused ever by the underlying logic that is different from the interpretation at times, or counterintuitive to interpretation. It's very important to realize that it's opposite direction. It doesn't mean that it's going to be an opposite direction interpretation. Now, when you've got the two parallel lines to the main influence arrow, this means that there's a time delay. That means that whatever is considered to be regular time or appropriate time passage for the dynamics represented on the influence diagram, the two parallel bars are there to indicate that there's a long time delay before the effect will be felt based on a change in the cause. Now, depending upon what literature you see or have access to, each feedback loop is supposed to have a polarity. It's either going to be a reinforcing loop if all influence within that feedback loop are positive, or if the number of opposite direction influences are even. A little bit like the rules of multiplications. Now, if there's an odd number of negative influence within a feedback loop, then what you see is balancing feedback within the system. These are some examples of causal loop diagrams. For example, here we see that there's a desired stock level and there's an order fulfillment delay that impacts ordered stock. So what happens is, as stocks are being ordered, there will be more delivery to the stock, and therefore if the stock level increases, then the ordered will be diminished. And therefore we have a simple balancing loop there at the center with an odd number of influences within the loop. Now, what we have here is a little bit more complex. Ordered stock increase the reception rate, and reception rate decrease the number of ordered stock. Now, the reception rate increases the stock level, and the stock level will decrease the order rate. And if the order rate increases, then the ordered stock will increase. Now, if we start looking at the number of odd versus even influences between those causal loop diagrams, what you will notice is there is an odd number of influences, and therefore the two of them are considered balancing loops. And as you flip through, you will see more examples that are actually happening there to illustrate some of the relationships. For example, on this one, on example 4, basically looking at supply and demand and the influence of the inventory on the price effect and the effect of price on the price effect and so on, only to illustrate that there's a series of balancing loops that are actually interacting and eventually causing economic cycles. So I invite you to take a look at these causal loop diagrams and try to determine on your own what could be logical influences and direction of influences, and try to make sure that you understand those relationships on these causal loop diagrams provided.